Howdy. That's for the Aggies that are out there. What I'm going to do is give you a quiz, if I can get this thing to work. Can you guys help me in the back there? Okay, this is a pre-test. The first question is, what industry has the largest fermentation capacity? Is it pharmaceuticals, wine, beer, or wastewater treatment? It's wastewater treatment, okay. How about which industry uses mixed culture fermentation? Pharmaceuticals, wine, beer, or wastewater treatment? Wastewater treatment. Would you employ a monoculture to treat wastewater? I think most people would say no. Should farmers employ monocropping? Most people would say no. And should you invest all your life savings in a single stock? I think you would say no. So the point of this exercise was to say that diversity is a good thing. Okay, so this is where we are right now. Crude oil sells for roughly $110 a barrel, and gasoline refined products is about $114 a barrel. So the so-called crack spread, the difference between the refined product and the raw material, is only about $4 a barrel. Now, if we have biomass at $60 a ton, on an energy basis, that's equivalent to oil at $20 a barrel. And so the crack spread is much, much larger. But the challenge is what goes into that circle. So people have been looking at this problem for many, many years. And I'm going to give you kind of a mini course on biofuels. The column on the left is various feedstocks. The column on the right is different fuels. And the column in the middle is the key intermediates that you have to go through. And we have chemical routes and we have biological routes. Okay, so let's take some examples. In the United States, we have soybeans. We extract out the fatty acids, react them with methanol to make biodiesel, which is an ester. And here you see the soybean plants. There's really actually not very many soybeans per acre. In the tropics, they use palms, which is exactly the same. And you see here, this is much more productive. It's about 10 times more oil per acre. As in the research stages, we're doing algae to do the same thing. Here's some algae farms. In Brazil, they take sugar cane and extract out the sugars, ferment that to ethanol. So here you see some shots of the industrial scale processing of sugar cane. In the United States, we use corn. Amylase enzymes break down the starch into sugar, which is fermented to ethanol, a typical corn ethanol plant. And every one of those dots is a corn ethanol plant in the United States. If we take lignocellulose and heat it rapidly, we get a bio-oil, which can be upgraded to hydrocarbons using hydrogen or other reactants. And so this is a shot of the bio-oil. As we described earlier, it's very acidic and water-soluble. We can take the lignocellulose and react it to make synthesis gas, carbon monoxide and hydrogen, and there use catalytic routes to make fuels. This is an old process. They used it to make kern coal into fuel during World War II. And then we can also ferment that synthesis gas into alcohol. And Cascada is one of the leading companies that does that. Interestingly, they have stopped their research in biomass, and they're going to natural gas as their source of synthesis gas. We can use acids to break down the lignocellulose to make sugar, and then ferment the sugar. One process uses extremely concentrated acid and has to separate the sugars using chromatography, which is a very expensive process. And then many, many people consider cellulase enzymes as the way to make sugar from biomass. And this is an artist's concept of the cellulase enzyme adsorbed onto the cellulose surface. Some people believe that they can take the sugar and directly go to hydrocarbons. And this is still in the research phase. When you visit their websites, you don't see any evidence that it's actually being commercialized. And the other process for taking the sugars to hydrocarbons uses chemistry. Virent is a spin-off company from the University of Wisconsin that's doing that, and this is their bioforming process. What we're doing is we're taking lignocellulose and using a mixed acid fermentation to break down the biomass to carboxylates, which are then chemically reacted to make various products. Of all these different feedstocks, the only one that has a chance of being successful to make fuels is lignocellulose. And so what I'm going to do is compare the two most common platforms, the thermochemical platform, the sugar platform, to our platform, the carboxylate platform. And what I'm going to do is compare all of these on a common basis. I'm going to use something that I call balanced biomass, which is about 68% polysaccharides and 32% lignin, which is a typical composition of poplar wood. What we can do is put that into the gasifier and then transform the synthesis gas into alcohols or hydrocarbons. Here you see the theoretical yields. We can take the sugars and make them into ethanol, as shown here, and then gasify the lignin to make ethanol, and that can then be converted into hydrocarbons. You see the theoretical yields here. And in our platform, what we're doing is taking the sugars and making carboxylates, and then the gasifier is used to make hydrogen, and the hydrogen is used to upgrade the carboxylates to make alcohols and hydrocarbons, and here you see the theoretical yields. All right, so if we summarize the yields, they're shown here. The two biological processes have the highest yield, whereas the thermochemical has a lower yield. And that's very easily understood because you're partially burning the biomass, and so that energy is not available to make fuels. Now, if we look at the catalytic step, which is highlighted here, you see that it's very difficult to transform synthesis gas into alcohols. That's still a subject of research, but it's very, very easy to turn synthesis gas into hydrogen. Every oil refinery in the world is doing that at a commercial scale. So if we complete our comparison, the thermochemical route, in my opinion, has some severe challenges. The sugar route is pretty good, but it has a difficult catalytic step if you want to use all the energy content of the lignin. But the carboxylate route has advantages in both cases. So for that reason, I've devoted my career to understanding more about this carboxylate route. And with that as a little background, I bring you to the title of my presentation, which is the MixAlco process, which we use to make fuels and chemicals from biomass. Okay, so here's a schematic view of the MixAlco process. We take the biomass and treat it with lime to make it digestible, and then we directly ferment that to carboxylate salts, remove the water, and thermally convert those salts to ketones, hydrogenate them to alcohols, and then upgrade those alcohols to hydrocarbon fuels. So I'm going to step you through the process, talk about the pretreatment. Now, there are a number of things that affect reactivity biomass, but these are three important ones. The lime pretreatment addresses the first two. And the idea is very simple. You just build a pile of the biomass on a gravel bed that's lined with plastic. The lime makes the biomass alkaline. You put water on top of it, blow air through the pile of biomass, so the combination of water, oxygen, and lime takes out much of the lignin. And so this is a photograph of a large pile of biomass in Argentina. These are people on the top, so you get a sense that people have built very large piles of biomass. It's done by making aqueous slurry. The liquid drains away and the solids accumulate in a pile. This is some early data that we took some years ago, looking at the advantage of having air versus no air. Bagasse is about 24% lignin. Without any air, it drops to about 17% very quickly, and then nothing more happens. But if you have air present, the lignin content just keeps dropping and dropping and dropping. Now, the physical structure requires mechanical treatment. And the classic way of doing that is a ball mill, shown here. The yellow is the biomass, and you just kind of beat it to death with these balls that are pounding on it. And what I'm showing here is some data that we took some years ago. All the columns on the left are without ball milling. On the right is with ball milling. This x-axis is the enzyme loading, and the y-axis is the amount of sugar that you get. And we have data at 1 hour, 6 hours, and 72 hours. So what you see is that in all cases, we use the same enzyme loading on the left and right. With the ball milling, we go from about 55 to 85%, so you added 30% reactivity. And that pattern is repeated over and over again, regardless of the time. The mechanical treatment adds about 30 percentage points to the digestibility. What I'm showing here is a result of a decade of study, a group called the CAFE group. What I'm trying to do is show various different pretreatments. Each of these symbols represents different pretreatments. On this axis is the overall yield, how much sugar you get per biomass, and this is how much sugar you get per unit of protein enzymes. And where you want to be is in the upper right-hand corner, and the only one that got there was this combination of lime and ball milling. Okay, so ball milling is fantastic, but it has a problem. It's very expensive. It costs about $430 worth of electricity to process a ton of biomass. And so we have a solution, which is to shoot the biomass. We're from Texas, so we have lots of guns. This is a slurry of biomass. There's a cone at the top, there's the gun barrel, and literally there's the shotgun shell. Here you see the cone, there's the shotgun barrel, there's the shell loaded into the barrel, and there's the firing mechanism. So what I'm showing here is results of our experiments with 5 different biomass sources. The left is untreated. The next one is oxidative lime treatment, and then we have oxidative lime plus ball milling, and then plus the shock treatment with the shotgun shell. And what you see is that the mechanical treatments do add value. You get more sugar compared to oxidative alone. And in this particular case, in 24 hours, the shock treatment actually did better than ball milling. When we went to 72 hours, the ball milling actually went a little bit ahead, but they're roughly comparable to each other. This shows in a rumen environment how much digestion you get. Corn is typically fed to cattle. What you see is it's about maybe 85% digested in 2 days. Alfalfa is digested about 60%. Now, if you feed raw corn stover, it's not very digestible, and if you look at the slope of that curve, it's rather shallow, so you don't get the rate of digestion that you need. But when we combined shock treatment with lime treatment of corn stover, you see we got about maybe 70–75% digestion, and if you look at that slope, it's very similar to what you have with corn grain. So what we believe we can do is take a waste material, corn stover, and upgrade it to be almost as digestible as the corn grain itself. Next, we have the fermentation. Basically, what we're trying to do is scale up a cow. There's lots of places where these organic acids form, as I've listed here. And you might ask, why does nature prefer organic acids rather than alcohol? Well, if you look at the Gibbs free energy change, the cells get more energy by converting glucose into organic acids than they do making alcohol. Now, this is a little bit simplistic. You also get higher acids. You get methane and hydrogen. We don't like methane. It's a waste product, so we put inhibitors in to knock out the methanogens. This simply shows that depending on the temperature, you can change the spectrum of acids. At the temperature of a cow, you get some of these higher acids, but at elevated temperatures, you get almost none of them, and it shifts towards acetic acid. Okay, now what we have to do is remove the water from that fermentation broth. I've looked at a number of methods. The one I prefer is vapor compression desalination. You take the saltwater brine. In this example, it's at 100 degrees, 1 atmosphere. The steam is free of salt. You compress that, in this case, to 1.04 atmospheres. It's at a higher temperature. You let that steam condense so it comes off as distilled water, and the heat of condensation becomes a heat of evaporation over here, and so that cycle will just repeat. So the heat of evaporation is recycled, and what drives the process is a small amount of shaft work that's invested in the compressor. One of the keys in making this work is you have to have really good heat transfer coefficients. Normally, when water condenses on a metal surface, it forms a film. Here's the measured heat transfer coefficient. We've learned how to put a hydrophobic coating on the metal, so we've raised the heat transfer coefficient by about a factor of 20, which makes the process much more economical. And so this technology has actually been demonstrated at a pilot scale. Here you see the 5 heat exchangers, and on the upper deck, you can see the compressor that drives this whole process. Once we have salts, we're going to thermally convert them to ketones. This is the chemistry as you see here. This takes about 20 minutes if you're going for 99% conversion, and this is one way of doing that in an industrial scale. Once we have the ketones, we hydrogenate them, make alcohols. Everywhere you see the ketone group, you can transform it into corresponding alcohol. This can be done in the liquid phase with a Raney nickel catalyst, and we use 3 stages for that. And then finally, once you have the alcohols, you can oligomerize them into hydrocarbon fuels. This is the chemistry. First, you dehydrate the alcohol, pulling out the water. Now you have a reactive double bond, which will oligomerize and grow the polymer chains. And then finally, if you want to, you can saturate those olefins to make the saturated hydrocarbons. This is the first liter quantities of material we made from our process. On the left is the alcohols, and on the right is the hydrocarbons. The date is January of 2010. Those of you with good eyes can actually see the date there. This is the composition of the hydrocarbons. The higher molecular weights can go into jet fuel, and the lower molecular weights can go into gasoline. All right, so what are the advantages of this technology? We can use wet feedstocks, so that makes harvesting very easy. We can use a wide range of feedstocks. Here are some examples. I'll spend a little time on energy crops. These are three examples of energy COPs. The one we use right now in the United States is corn grain. So this gives you the idea of that. And I pulled this picture from the web because Philip is holding an ear of corn in his hand. You see all that biomass in the background, and all you get from it is a stinking handful of grain. And so if the United States said we're going to supply all of U.S. gasoline consumption from corn, that land area would have to be planted. Plus, we have this horrible moral dilemma of competing with food for fuel. Now, sorghum is much more productive. This is a shot taken in November. It was planted as a seed in March. So from March to November, it grew that tall. And energy cane is another crop that can grow in Florida and South Texas. This is 1 year's growth, and here you see it harvested. So it's a massively productive crop. We can also use municipal solid waste, which is shown here. Take the energy of garbage and use it to fuel your car. Those of you that know movies are probably familiar with this scene from Back to the Future. Okay, so we're very energy efficient. What I'm showing here is the energy it takes to distill ethanol is about 28% of the energy content in the ethanol has to be devoted to the distillation, where only about 2% of our energy content has to be devoted. We don't require genetically modified organisms. We take what nature gives us. There's lots of products that can be made. My main emphasis is fuels, which are shown down here, but many classes of industrial chemicals can be made as well. We can also do something called distributed processing. Each of these circles represents a farm. On the farm is a fermenter. You truck the biomass to the fermenter. The liquid fermentation broth is piped to a central facility where you upgrade it to ketones. Those ketones are then brought to the refinery where they're hydrogenated and made into gasoline, which is shipped through the existing pipeline system. Importantly, we do not require the addition of enzymes, which are very expensive, and we do not require sterility, which is also expensive. So all of that has an impact on the economics. Our base case is about $2.56 per gallon, of which you see 60 cents of that is the biomass. What I'm showing here is the economics as a function of scale. Each of these colors is a different biomass feedstock cost, and this is the selling price of the gasoline product. And then this red curve is the capital cost of the plant. So let me just point out a few spots on this for you. This is the base case, which is 40 tons per hour. As I mentioned, it was $2.56 per gallon. If we go to a very large plant, which I call an energy plantation, it drops to about $1.76 per gallon. And that $1.76 per gallon corresponds to crude oil at $63 a barrel. So what I'm suggesting is that as long as crude oil is over $63 a barrel, making biomass into gasoline is simply cheaper. Okay, a little bit of history on our process. I started working on this technology in 1991. In the year 2000, we built a pilot plant located on campus, which you see here. And then in 2008, our commercialization partner, Terrebonne, started building a demonstration plant, and then they partnered with Valero and Waste Management. Now that sounds terrific, but last November, or actually last September, Terrebonne had to declare bankruptcy, and so they're out of business, but fortunately, Earth Energy Renewables has purchased their assets and is trying to take the ball to the finish line. This is the first engineering drawing of the fermentation system. It's a pit dug in the ground, covered with fabric, lined with concrete. And so here you see the pit being dug, lining it with concrete. And then these are the tanks that store the fermentation broth. And then there you get a sense of scale. And then this is inside the fermenter with the fabric cover and the concrete lining. And then this is what it looks like on the outside. And the next shot is an artist's concept of what it should look like to take advantage of the fact that we're scaling up the cow. We had a dedication in November 2008 where Governor Perry there spoke, and they even let me speak to the group. And these are the gentlemen who founded Terrebonne and built the plant. And here's the Holtzapple family posing with Governor Perry. And I took him inside the fermenter and explained what's going on. I like this photograph because my son, John, is looking into the future. So here's the kind of a summary. We do not require any scientific breakthroughs. We believe this technology is commercially ready. I've highlighted these two conditions right here, where we make our hydrogen from the undigested residue. You've seen these numbers before, $2.56 a gallon, $1.76. In the near term, what I think we'll do is use garbage, which has a tipping fee, and we'll make the hydrogen from methane, and in that case, it's very inexpensive, about $1.24 per gallon. Okay, we had a pre-test, now we have to have a post-test. See if you learned anything. Should we encourage diverse approaches to biomass conversion? I hope you'll agree with me that the answer is yes. Okay, well, where do we go from here? This is a project that was funded by DARPA. In 2009, the phase one was $20 million. The objective was to make 100 liters of jet fuel at the pilot scale. And then in 2010, we went to phase two, which was a $17 million project, the purpose of which is to make 6,000 liters of jet fuel. And hopefully in the future, we'll move to a commercial plant, which would be phase three. Now, this DARPA project, the DARPA is famous for having contests. And so what they did was they started with 21 different organizations, each with their favorite biomass process. But in order to stay funded, you had to produce 3 liters of jet fuel every 3 months, 2 liters every 3 months. And the only organizations to survive that were Texas A&M, Terrebonne, and General Electric. The way it worked was we made the alcohols and sent it to General Electric, and they produced the jet fuel from that. So the carboxylate platform was the only one to survive this contest. Then in phase two, DARPA insisted on having 2 organizations start, but you still had to meet milestones, and the only one to survive that was Terrebonne. But as I described, they have gone bankrupt, and so the idea is for Earth Energy Renewables to take up the ball and complete the project. Oh, that's interesting, the animation didn't work. Okay, computers failed me. If the computers worked, what you would see here is an animation of an engine that we project to be about 60% efficient. This is my other hat. I'm an entrepreneur and have started a company called Star Rotor Corporation. So what I'm going to show here is the impact if that engine is successfully introduced to market. This is a conventional car getting about 30 miles per gallon. Going from New York to Los Angeles takes about 93 gallons of gasoline. And if we grow sorghum to produce that gasoline, this is a land area that would have to be grown in sorghum. Now, if we were to take the Star Rotor engine and put it into an automobile, it'll get about 90 miles per gallon, and our cross-country trip now takes only 31 gallons of gasoline, and you shrink the land area by a factor of 3. If you take automotive technology to the extreme and go with the car body called the Precept, this was a concept car developed by General Motors in the late 90s. If you were to put a Star Rotor engine in it, I'm estimating you would get about 144 miles per gallon. So a cross-country trip from New York to Los Angeles would take only about 20 gallons of fuel, and you see that the land area required to supply our transportation system is quite small. Okay, so this is my last slide. It shows the vision. This is what I've devoted my life to doing. We would produce crops which go to the local MixAlco process where we produce ketones or acids. Those are then brought to an oil refinery where they're upgraded to make gasoline or alcohols. The hydrogen needed for the upgrading would come from natural gas. Then what we do is we take the gasoline, put it through existing pipelines, existing gas stations, and existing automobiles. Now, when carbon dioxide is emitted from the tailpipe, through photosynthesis, we recycle it back as new plant matter, and so what we've done is we've completed the carbon cycle. Now, notice that we're actually using natural gas, an abundant resource in the United States, but we're turning it into hydrogen, so only the hydrogen is attached to the biomolecule, which you can think of as a hydrogen carrier. The carbon dioxide is present in a central location, so if you're concerned about global warming, what you can do is sequester that CO2 and stick it under the ground. So what I'm showing you is a way that we can use our abundant natural gas reserves, but in a way that does not contribute to global warming. And with that, I'd like to close, and hopefully you have some questions. Thank you for your attention.
Questions?
Hi, thanks for the good talk.
I'm just wondering how much do you spend in the dewatering part, the removal of the water, because anaerobic digestion or the action of the anaerobes on the biomass has a limitation. That is, there is a low concentration of carboxylates that the anaerobes can tolerate. I think that it's around 10 grams per liter of the carboxylates that the microorganisms can tolerate. So you need to remove a lot of water before you can process it thermochemically. So
you're mistaken. Using food scraps, we've gone to 100 grams per liter of acids. And using other biomass resources, we've gone to 50 grams per liter. In fact, if you speak with Tyler Mann, who's here in the audience, one of my graduate students, he's gone to about 70 grams per liter. Now, industrially, what you shoot for is the economic concentration is on the order of 20 grams per liter, 25 grams per liter. But the dewatering is a very, very important part of the process, no doubt, and that's why I put a lot of effort into figuring that out. The vapor compression technology is extremely energy efficient. Because you're operating at such a small delta T, it does not take very much compression energy to raise the pressure. So if you recall, I showed a slide. Ethanol distillation takes about 28% of the energy content of the ethanol. Our process takes about 2% of the energy content of the acids.
I'm very interested about the fuel price you proposed. It's quite low, and last year I remember that I read a report from CNN. It's saying that the U.S. Navy and the U.S. Air Force purchased the biofuel at the price about $18 per gallon. Mm-hmm. And did you consider about the capital investment and all the other costs in your price?
Absolutely. The costs that I give are completely loaded: labor, maintenance, utilities, profit. It's fully loaded. When we went to phase 2, the only way we could go to phase 2 was if DARPA believed that we could make these fuels at under $3 a gallon. So the fact that we went to phase 2 means that the government's independent economic analysis believes that it can be done for under $3 a gallon. Now that's at a commercial scale. You know, if we build small plants, then it costs $20 a gallon. I think.
Let's see, we've got one here, and then Lonnie.
Is this on? Thanks for the wonderful talk.
You're
Andrew
welcome.
Lepore from University of Tennessee. I was interested in the vapor compression system. It was used on desalination, but I was wondering, in your step, would you have any corruption or loss of thermal conductivity because you have a complex mixture?
Well, so far we haven't practiced that at industrial scale yet, so I can't answer that question with certainty. But the hydrophobic coating actually has Teflon in it, so that's a low stick surface. And actually at the pilot plant that we had at Laredo, they did not see any scaling effects from the pilot studies there.
Okay, thank you.
You're welcome.
Mark, we got one left.
Yes, Lonnie.
A great talk.
Thank you, sir.
I wanted to also say we have no trouble getting over 100 grams per liter of organic acids, as long as you keep them neutralized. But I was wondering, in your calcium system, are you recirculating until all the calcium has been consumed for neutralization, or you add more calcium to increase your levels of carboxylates?
Thank you for asking that question. In the ketone step, calcium carbonate comes out of that, so that's simply recycled back to the process. We don't have data to show this, but Tyler Mann, who I mentioned before, has been looking at the effect of cations, and many, many cations work. It turns out calcium is actually the worst. Magnesium, sodium, potassium, and ammonium work much better. So as our technology continues to improve, we'll be shifting towards other cations.
I think we'll get on to Lonnie, but let's thank Mark.
All right, thank you.